Good. I think we should start given the time. Welcome everyone to this edition of Verifiability Talk. It's my honor to introduce Ajitha Rajan, who is our speaker today. She got her PhD at Minnesota University, if I remember well, and has been at various very nice places like Grenoble and Oxford. And now she is an assistant professor at the University of Edinburgh. She has done lots of very interesting work, for example, on testing AI systems and all sorts of very interesting stuff. But today she will be talking about testing GPUs and smart contracts. Ajita, thank you very much for having accepted our invitation. This meeting is being recorded. If you don't want your name or initials be recorded and later post on YouTube, you could also join the meeting using a guest ID, so you don't have to put your actual name. Otherwise, we will post this later on YouTube. Thank you very much again, Ajita, and the floor is yours.
Thanks, Mohammed, for the introduction. Thanks, everyone, for taking the time to attend this talk. So I'm going to briefly introduce myself, despite Mohammed introducing me. So I'm a reader or associate professor at the University of Edinburgh at the School of Informatics. So the reason I keep looking down a little bit is because I have this other screen that I hope to write on. So pardon me if I don't look at you or all the time. So that's a strange thing with these virtual meetings, unfortunately. So my research is primarily in the area of software testing. I've dabbled a bit in formal verification, but really am a hardcore testing researcher and software engineering in general as well. So my research group currently, I have about 7 PhD students, and we also have several master's students contributing to various parts of our projects. So I'll tell you a little bit more about my research interests before I dive deep into the GPU testing and smart contract testing topic. The thing with the terminology of software testing is people have different interpretations of what a test means, what is an oracle. So just to clarify and to make sure all of us are on the same page, I'm going to quickly go over some concepts. So bear with me. These might seem trivial to you, but it's just to make sure everyone understands when I use certain terms. So I'm going to broadly classify software testing as 4 different tasks that you see here. So test generation, which is the task. When people say test generation, they typically mean input generation, test execution. So test usually includes input. It includes the actual output that you get from executing your system. It also includes a comparison between actual and expected output, which is what the test oracle is. And that determines whether your test passes or fails. And then you have this notion of test adequacy, because testing is typically an incomplete technique. You don't exhaustively sample your input space, and it's for complex systems, this is not feasible to do so. So it's inherently incomplete. So you need a way of knowing when to stop. So in industry, typically people stop testing when they run out of time or they run out of money. And that's not the ideal way to stop testing. So it's good to have an objective metric that tells you when to stop testing. And this is what test adequacy is about. So just very quickly, just to show you an example to put things into context. So here I have a JUnit test. Obviously, this is a unit test, but you have other forms of test, and I'm only using it as an example here. This is a test for a cruise control system, say. First, you set up your environment and test inputs. Okay, so this is what an input is, really, test inputs. So when people talk about automated generation of test inputs, they try to see how to come up with these values in a way that respects the environmental constraints and your input constraints. And then you call the function under test. Here, the function under test is the cruise control system, and you call it with the inputs that you've set, and that gives you the actual output. And to determine whether the test passed or failed, over your system, you have an expected value. We'll come to how people come up with expected values a little later on. But let's say you magically have the expected output of the system. Then a comparison between the expected and actual, which in this case is an exact equals comparison, but it doesn't have to be, tells you whether the test passed or failed. So if your actual equals expected, in this case, the test passes. So this comparison and the expected output is what a test oracle is. So how do people do input generation? Typically, you want to try and cover your input and output space in a clever way. Like I told you before, it's not possible to do it exhaustively. So traditional techniques look at property-based testing, which is how do I make sure I've tested my specification and requirements as thoroughly as possible? Or how do I partition my input and output space using those specification and requirements, and then sample those partitions in a way that you've tested all the boundaries and all the partitions adequately. There's also combinatorial testing does something similar. People also use fuzz testing, which is mainly driven by random mutations and changes to your inputs. People find it very effective because it's very fast and you have lots of inputs. Other ways of input generation is covering the structure of your program or model. So the first part was really black box without looking at your program or model. And the second technique here is looking within your program or the structure of your implementation and making sure you cover the different structures as well as possible. And some techniques to do that are model-based testing, coverage-based testing, mutation testing, symbolic and concolic testing. Test adequacy that I mentioned earlier, people typically use coverage metrics as a means of knowing when to stop testing and how effective your tests are. So they look at how well have I covered my program. If I've covered if the tests execute all the statements in my program, then I deem my tests are adequate with respect to statement coverage. If you've covered all the branches, then you deem it's adequate with respect to branch coverage. So these are some common metrics that's used to assess effectiveness of your tests and also when to stop testing. So you can have metrics based on specification, code, model, or you can have simulated bugs and see how good your tests are in uncovering these bugs. And very quickly, test oracle. It's a difficult problem, as you might imagine. Coming up with an expected output from just specifications is, if you have a well-defined set of specifications, like in the avionics domain, for instance, it's possible, but not every domain has a well-defined set of specifications. So coming up with this is very difficult. So people rely on domain expertise a lot. So this is still largely a manual process. So what people have done is relied on implicit oracles, which is essentially if my program crashes or if I have buffer overflows, then I clearly know my test failed. But for all these other conditions, other sorts of functional failures, you don't really know unless guided by an expert. There is some work on how you use specifications and documentations and metamorphic relations to guide you in determining when a test fails automatically, but this is still largely research in progress, and the test oracle problem is not considered solved yet. So if you are looking at an interesting testing problem, this might be a good area to pick up on. There is a lot of literature on it. There's a lot of interesting work on it, but this is not going to be a topic today, unfortunately. So why am I talking about all of this? It's just to kind of shed light on where my research is. So I'm going to categorize it under these 4 topics that I talked about. So I've done a lot. So software testing research really is about how do you automate these different aspects rather than relying on humans. First of all, testing is a boring process. Nobody really wants to do testing. It's tedious, but it's important. So we definitely need to do it, but we want to get away from the boring, tedious task and try and automate it as much as possible. So that's what the research in this area is all about. And automating test generation, I've showed you some traditional testing techniques. So the work that I've done is really on GPU kernels, smart contracts for blockchains, Android GUI testing, and more recently, we've started looking at testing AI tasks in self-driving cars. In the past, I've also done automated test generation for safety critical systems in the avionics domain and in embedded systems in general. I've also looked at coverage metrics as a means of test adequacy. My current work looks at GPU kernels and smart contracts. I've looked at test oracle problems. So we've looked, like many others, we've looked at how we might use neural networks to automatically classify these tests as pass or fail. And we found that Well, neural networks are maybe a step in the right direction, but it doesn't completely solve it because it still needs label data. So you don't completely get away from the manual task. And finally, we've also looked at how can you execute tests effectively, because people accrue tests by the tens of thousands. So they take up a lot of resources in execution, and people, because resources are available cheaply and you can just launch your tests on hundreds of servers, that doesn't mean that that's the effective way to do it. It's not environment friendly either. So we've looked at some work on how we might order tests to use cache effectively, and how instead of CPU resources, we might use GPUs to parallelize test execution. Anyway, so this is just to show you what work is in my group. But the focus of the talk today is GPUs and smart contracts and our testing work in that domain. I know I kind of went through this very quickly, and I apologize because I have a lot of slides after, and I thought, okay, if I spend too much time in the introduction, I'm not going to be able to cover anything of what I planned. But do you have any questions? Okay. So just because I'm flying through things, don't hesitate to ask me questions. Feel free to interrupt me. I prefer taking questions as I progress rather than at the very end. All right, so our first topic today is automated test generation for GPU kernels, in specifically GPU programming model OpenCL kernels, and we use fuzzing and SMT solving for automated test generation. So before I start talking to you about automated testing for GPUs, I thought I should motivate why I am presenting GPUs for this task talk. So I have this obligatory slide, I feel, so that people feel like, okay, GPUs should be relevant for tasks. So recently I've started working on this project with CodePlay, where they develop they facilitate launching GPU kernels for people who know nothing about GPU programming. And if you take AI, and these are for self-driving cars is the domain that they're working on. So if you take that domain in self-driving cars, there's a lot of reliance on AI tasks, especially for perception. So in particular, so I've only presented perception here, but obviously you have for planning as well. But perception, if you take perception tasks like semantic segmentation, object detection, lane detection, pedestrian detection, all of these tasks require a lot of resources, and it's quite common to launch these tasks on GPUs. When people test AI tasks, they test whether the neural network architecture does what it's supposed to do. You do your adversarial testing and you check the output. But there's very little testing that's focused on whether the code that you've written and then launched on the GPU works correctly. So there is this intermediary step where after you've built your AI architecture, you take that and you deploy it on the GPU. So which means you take your CPU code and convert it into GPU code. People don't usually write this GPU code. They rely on libraries to do it for you. So there's a library that does this step, that takes your Python code or whatever it is and launches it in OpenCL so it can run on GPUs in parallel. But what we're going to focus on today is not whether the person who wrote the Python code has done it correctly, but whether the translation to OpenCL has been done correctly. And that's where it's important. And you might think, do people even make mistakes in this translation? Do I even need to care about it? So there is this paper from ICSI 2020, which is titled Taxonomy of Real Faults in Deep Learning Systems. And they've categorized commonly occurring faults in deep learning systems. It's definitely worth a read if you are in this domain. And they found that GPU errors is one of the 5 main categories of bugs in deep learning systems. And it's because of misinterpretation on how to use GPU APIs, or data races that because of the memory architecture within the GPU, or incorrect use of parallelism. There's also timing errors, but we're not really going to go there today. But so GPU bugs do happen. with deep learning, and it is definitely worth testing for these errors because it can certainly have an impact on the functionality and can lead to potentially crashes. So I hope I've convinced you that GPU testing is needed for tasks. But if not, I think we're going to have a conversation after so that you give me a chance to convince you. So why is testing for GPUs different from CPUs is the next thing that you need to understand is GPU architecture is very different from CPU architecture, especially the way execution happens and the way the memory is organized. So here in this figure, I've shown that there's 3 levels of memory organization. So you have this global memory that all threads and all work groups can access. So before that, I think I should say what a work group is. So imagine that you have a classroom and you have several rows of benches, say, where students or pupils are sitting. And each bench has to work together at the same time. So it's like they have to hold their hands and take a step together always. No one can just walk off themselves. So, but the different benches can do different tasks. That's completely fine. But every bench, all the pupils in that bench have to hold their hands and be synchronously take their steps at the same time. While the other benches have the same constraint, but there's no constraint between the benches. So that's how, so the work in that example, a bench would be a work group where within a work group, you have 32 to 64 threads, and all of these threads have to execute the same instruction at a given clock step, at the same time step. And after that instruction is executed, once all the threads have completed execution, then you execute the next instruction. So it's called the SIMT model, which is single instruction, multiple thread. So all the threads within the same work group always execute the same instruction. So what happens if there's an if? So if you have if A equals B, let's say, and let's say threads 1 to 4 satisfy the then branch, but thread 5 to 7 here takes the else branch, let's say, which is something else. Then what happens is that when threads 1 to 4 takes the then branch, thread 5, 6, 7, and 8 do nothing. They just wait till the then branch is completed. So the then branch will be completed. This does nothing. It just waits. And then the else branch happens, and these 4 threads do nothing. And then they get synchronized again once the if is completed, and they start executing instructions together. So that's how it works. And the threads in a work group access a local memory together. I have another figure for this. So threads in a work group access the same memory called local memory, and threads across work groups, if they need to access the same memory, it's done through the global memory. So as you can see, I'm setting up for a data race. So the problems that are peculiar to OpenCL programming or GPU programming is you can have intra-work group data races, so data races in the local memory, or you can have inter-work group data races, which is data races from threads in different work groups, so data races in the global memory. You can also have barrier divergence, which is the if example I gave. But in the if you have a barrier, which is a synchronization statement, then one set of threads in a work group might, a barrier makes you wait till all threads have executed that barrier in that work group. So one set of threads will wait for one barrier, but another set of threads might wait on a different barrier, resulting in barrier divergence, and your execution doesn't proceed beyond this if statement. So this is again another problem that is specific to GPU programming. So CPU testing techniques do not handle this. So we do need particular GPU testing techniques that's aware of the execution model and that's aware of the memory organization. So obviously, we're not the first ones to think about this. There is related work in this. There's static analysis techniques. but they have been known to report more false positives, and they don't handle certain constructs, synchronization constructs, and they don't handle the floating point data type, which is also a concern because a lot of GPU programming is done because they're good at handling floating point operations. So there is some existing work, but it doesn't support inter-workgroup data races either. So that's where we come in. So our goal is to generate inputs. We do it using a combination of black box fuzzing and SMT solving. We also do this other cool thing called schedule amplification, which I will show you, which helps us detect inter-workgroup data races. So here's a schematic of our approach, where this is the input given, an OpenCL kernel. You can find our tools at this GitHub link here. Feel free to access it and play around with it. We're happy to receive feedback as well. So we've, I think I forgot to mention where our papers were published. So we published our coverage measurement framework for OpenCL kernels in phase 19, I think. And we published our testing work in GPU workshop in 20. So we take an OpenCL kernel, and then we automatically generate inputs for this OpenCL kernel using black box fuzzing. And we take those inputs and we check how much coverage we achieved over the kernel. And we have different types of coverage we measure. We measure branch coverage and we measure barrier coverage. If adequate coverage is not achieved, then we give it to an SMT solver. We use the Z3 solver. And the solver then covers the remaining branches that the black box fuzzer was not able to cover. And we take all of these inputs, we combine the inputs from the fuzzer and SMT solver and give it to a schedule amplifier, which is in addition to this execution engine, executes the inputs with the OpenCL kernel on different workgroup schedules and checks if any data races or barrier divergence is found. So that's the general workflow. And I will walk you through the testing techniques quickly. So how does the fuzzing technique work?
May I ask a quick question?
Mm-hmm.
So about barrier coverage, is it not the case that you by default cover all barriers when you run through an OpenCL code? How you could miss a barrier in OpenCL code?
So in OpenCL code, like I mentioned, it's when you generate people do have if statements. So if you assume there are no control flow branches, then what you're saying is absolutely right. You will cover all the barriers. But if you do have control flow statements embedded within, it's not clear that you will cover all barriers. So in our examples, I think what your intuition is absolutely right. So we did find for many of our kernels, we achieved 100% barrier coverage very easily, but there were kernels where we did not achieve 100% barrier coverage. And these were the cases where you had if statements and maybe certain ranges of inputs only covered the then branch or only the barriers within the else branch, but not both. Okay. So then you would have to generate specific inputs to cover those barriers. So it's generally not good practice to have control flow statements in GPUs, but because they're being used for general purpose programming so widely these days, you do have control flow statements.
Thank you.
Okay. So how do we do fuzzing? The fuzzing technique that we've implemented is a very naive approach to do black box fuzzing. There's nothing fancy here. So what we do is based on the kernel arguments, we generate random values for those arguments. And then we pick a random seed and we execute it and check how much branch coverage it achieved to begin with. We add this seed to the test suite. Obviously, this is the first test, so it does achieve some branch coverage, assuming, and we add it to a test suite. If it gives any extra branch coverage, so the first seed is automatically added. Then we pick one of the tests from the existing test suite and you mutate the values. So let's say you had an integer input, 10, you would mutate it and it might become 20, let's say. And then you execute this new test with the mutated values and check if you got any additional branch coverage. If there's any additional branch coverage, then you add it to the test suite, otherwise you discard it. and pick another seed from your existing test suite and mutate it again. So you keep doing this. So obviously this is a very naive approach, but it's very quick. So you can end up with a lot of tests in a matter of seconds.
Sorry,
so the limitations of
one more question. Can you do this process on a CPU, or do you do it necessarily on a GPU?
So the fuzzing itself is, so the technique, our fuzzing technique, you're asking? Or
oh, I think this whole process of like concolic going through the whole thing could be done also on a CPU, couldn't it? Or...
Yes, absolutely. Absolutely. We, in fact, so all our implementation is in LLVM Clang, and we do it on a CPU. Mm-hmm. So it's just the tests are, once the tests are generated, is executed on a GPU, but the fuzzing technique itself is done on a CPU.
Thank you.
So as it's well known that fuzzing is not perfect, and it's particularly has difficulties in if statements where you check for specific values like here. So if x equals minus 2987, the probability that you'll pick an input x with exactly this value is very low because you do random mutations. So fuzzing is not very good with such if statements. If you have deep control flow, even though that's not a good thing in GPU programming, it would still suffer as well. So that's where we use SMT solvers, where you check which branches. So assume that, let's say, this particular branch was uncovered, is not covered by fuzz testing. Then we capture the path constraint to this uncovered branch and give it to the SMT solver, and that will come back with the inputs to cover the branch. So as I said, we did this with the Z3 solver, and we feed the path constraints for the uncovered branches, and we check if we now cover the branch, which we should, because SMT solvers, unless it doesn't return an input, you do cover the branch. So the schedule amplification that I mentioned earlier, why do you need it? It's because in GPUs you have no access. They do not provide access to the workgroup scheduler. So scheduling the work groups is done in a non-deterministic manner by the GPU scheduler, and you are not allowed any control over it. So assume that you have 8 work groups that you're launching, okay? And these are parameters that you'll set when you call the GPU. You'll say, how many work groups do I want to launch? But assume that your number of GPU cores is only 4. You only have 4 GPU cores. So even if you launch 8 work groups, it can only run 4 at a time, right? So the way which 4 work groups should run first is completely arbitrary, and it is and it's done by the GPU scheduler, which is proprietary, and you're not allowed to look into it. So you might assume it does work group 0, 1, 2, 3, and then it does 4, 5, 6, 7. That's just one possible schedule, but because it's non-deterministic, the next time you run it, it might be a completely different order. So to kind of circumvent this issue and to see how your kernel does with different workgroup schedules, what we did is we built a layer over the OpenCL built-in functions, so that every time you asked for a workgroup, we would give we would have different orders of work groups, and we would spit out a work group ID based on the randomized order that we have, and we have several randomized orders. So as a result, using our schedule amplifier, so one possible permutation you might get will be work group 3526 is launched first, and then 4107. And because there's no constraints between these, you're allowed to do it in any order. So we try, obviously we don't exhaustively do all possible orders. So you can choose how many orders you want with the schedule amplifier. So in our experiments, we did about 20 random workgroup schedulings and checked if the program gave different outputs with different workgroup schedules. And if it gives different outputs, it means it's an instance of inter-workgroup data race. Any questions on this? Okay. So for our evaluation, we evaluated over 217 OpenCL kernels from common GPU benchmarks. That's shown here. And we ran it on my student just ran it over his laptop. And this was the OpenCL version we used. So the questions we asked in our evaluation were, is fuzz testing effective in this domain for GPU data races? And is there any use in using SMT solvers, or is fuzz testing good enough? What is the effectiveness of schedule amplification? So we evaluated both fuzz testing and SMT solver using branch coverage, but we also evaluated them using mutation score. So what that means is that we seeded artificial faults into the GPU kernels, and we checked if the test suites were capable of revealing these artificial faults. And you do that by comparing the original kernel and the fault seeded kernel. So on the x-axis here, I have the percentage of either branch coverage or mutation score, where branch coverage is shown in blue. Mutation score is shown in red. I see Mohammed peering, so I'm going to zoom in just so that it's easier. On the y-axis, I have number of kernels. So this is like a frequency bar, let's say. So you can see that about 186 of our kernels have 100% branch coverage. So, and this was just using fuzz testing. So the results here are just fuzz testing. It's not using SMT solvers. So this is 186 out of 217 kernels. So that's pretty good for branch coverage. But we did not get 100% mutation score for many of the kernels. Only about 70 got 100% mutation score, and the mutation score is more widely distributed. So obviously we want to increase both the branch coverage and the fault finding capability of the test suites. So we decided, okay, if we combine fuzz testing and SMT solvers, how did we do? So I'm sorry that the plots are all a bit different. So this plot here on the x-axis, it shows the kernels that did not have 100% branch coverage. So if I go back to the previous slide, all the remaining 31 kernels that did not have 100% branch coverage, you run SMT solvers on, because that gives you tests for uncovered branches. And we see that if you have SMT solving plus fuzzing, which is the blue, it does increase the coverage over the red, which is just pure fuzzing. So the mutation score is increased. You can see from 1% here to 75%. So there is a definite increase in most kernels that had uncovered branches, which later could be covered with SMT solving. So the mutation score did jump significantly. So there is value in using SMT solvers. That's all we wanted to establish with this experiment, was the tests with SMT solvers were actually useful in finding seeded faults. Oops. And finally, the schedule amplification that we did, where we had different random orders of workgroup schedules that were launched. We did find instances of inter-workgroup data races that were not previously found. So these are the kernels from different benchmarks where we found it. So that was useful to us as well. It shows that the kernels were sensitive to certain workgroup orders. So finally, the overhead that we observed was not too much. So fuzz testing only took about 2 seconds on average. SMT solving took anywhere between 0.2 seconds to a minute. Still not too bad. And the schedule amplifier did not introduce any significant overhead. So it's worth noting that GPU kernels are typically, at least in the benchmarks that we executed, were typically quite small. It's not that large. You don't find GPU kernels of tens of thousands of lines of code. If you do have one, send it to us, because we haven't managed to find one. So when I say 1 second and 2, the reason they execute so quickly is because the kernels are not that big. So in conclusion, we found mutation-based fuzzing combined with SMT solving is a good way to test OpenCL kernels. Schedule amplification helps uncover data races within work groups. So this is where we stand with the GPU testing work. I haven't presented it, so we're still trying to see how we can fine-tune it for AI tasks in particular. So this is still work in progress, and we've only just started this work to see how perception tasks like object detection will be affected by GPUs. So if you're interested in working with us on this topic, do contact me. Let me just keep an eye on time. So it's 4:40, and I should at least leave 5 to 10 minutes for questions. So again, here's the link to the tools. So I'm going to start the smart contract testing work, but I'm going to keep an eye on the time. So I might have to skip through some details, so forgive me if I skip through a lot of slides, but I'm happy to have a chat offline if you're interested in the work. So the smart contract testing work is led by my student Safer. Safer is in his final year of PhD and is about to graduate. So do contact him if you have any questions or if you're interested in pursuing the work with him. So what are smart contracts? I'm sure many of you have heard blockchains and smart contracts. So just to clarify, smart contracts, you can just consider them as programs or a bit of code. And so it's code and a state, which is the internal data that is used and the state that is recorded. So it's a computer program or a transaction protocol. And the advantage with smart contracts is that you encode conditions on when it should be executed. And whenever the conditions are satisfied, it gets executed automatically. You can see where I'm going with this. So how does a contract work? So first, people agree what transactions do we want on this blockchain, and you put it down in the form of code. You can think of it as just a traditional programming language, but with certain niche data types, function types, and certain other functionalities. But if you think of it as a regular program, it has some particular if statements and events that when triggered, when they are satisfied, the smart contract gets executed. So first you decide what those conditions should be. The contract is part of the blockchain. People who invoke the contract are anonymous. That's the advantage of the blockchain itself. The contract executes whenever the conditions are met. And when the contract gets executed, it's added as a block in the blockchain. So people have considered using smart contracts in autonomous systems because smart contracts are automatic. They're fast, they're direct, they're cheap, they're transparent, they're accurate. You need a good understanding of what the conditions are and when to execute the smart contract. But there are lots of advantages for autonomous systems. So there have been some recent papers that have considered using smart contracts for autonomous vehicles. So I've listed a couple of papers here. So this one in particular is quite interesting. It's when imagine a futuristic world where all of us are in our self-driving cars and one of us is in a terrible rush to get to our destination, and we are willing to pay others to clear the way so we can go. So you can have a smart contract that encodes this rule, which says that, look, if you let me pass, then I will pay you a certain amount of Ether or Bitcoins or whatever it may be. And so if you invoke that function, and you make the payment, then that person has to allow you to overtake. And of course, you might have distance rules and things so that you only invoke the function when another car is within that distance. So anyway, so there are ways in which smart contracts can be very interesting to autonomous systems. And there are several questions around it. But because smart contracts are transparent, and they have inherent privacy and anonymity, it's interesting from a trustworthy aspect as well. So here's an example Solidity contract within the Ethereum blockchain, a smart contract. So in this contract, so the contract is called Ether Lotto, which as it suggests, it encodes like a lottery system. So you have, whenever someone invokes the play function, if the random value that is generated, which is dependent on the block timestamp, so it's completely random. If the random value is 0, that means you've won the lottery ticket. And there is a transfer that happens. The bank takes a fee amount to, let's imagine that's the processing fee for your lottery ticket. And the remainder in the pot gets transferred to the person who invoked the play function. So it's a way of encoding the lottery rules. And the advantage with that is that it's transparent, there's no fraud. And if anything needs to be changed, everyone needs to agree that it has to be changed. So this is an example of a smart contract. But smart contracts are not without their own set of flaws. There's been lots of reports of vulnerabilities in smart contracts and attacks in smart contracts. And here are some popular ones. And here are some well-known smart contract vulnerabilities. I'm not going to go through each of these, but there's a lot of work on how do you verify and test smart contracts. And we are one among many who have developed techniques for testing smart contracts for these vulnerabilities. Sorry. So this is an example of a timestamp vulnerability. So the random variable that is generated uses the block timestamp to generate the random value, but you can have a malicious miner who has access to this timestamp variable and who might manipulate it so that they can set random to 0 and therefore win the lottery. So that could be a form of attack. And that happened, I think, in one of these, I think the governmental Ponzi scheme, where they manipulated the timestamp variable so that they could win the money. So those sorts of attacks can happen. So it's important to test and verify your smart contract. So first we started off, instead of developing a testing framework, we started off by saying, how do you first understand what's going on in a smart contract? Because if you take traditional programming languages, we have compiler frameworks that enable you to traverse the program, instrument the program, analyze the program in different ways, but there's no such facility for smart contracts. You have the Solidity compiler, but it doesn't allow instrumentation and analysis as easily. So we started building an instrumentation framework to begin with that allows you to query the abstract syntax tree, and you can also instrument assertions and things into that. So this is what the instrumentation framework looks like. It takes the Solidity contract, goes through the Solidity compiler to get the AST, and then we provide facilities to query the AST, modify the AST, and finally generate Solidity code back. So you can ask how many functions are there, how many functions of a certain type are there, generate call graph, control flow graph, plug in assertions for integer overflow, underflow. So those are the sorts of things we do. This again is just what I'm going to just keep this. So after doing this, we said, okay, we can now instrument it. There's lots of existing static analysis tools. There's also testing tools, and we built a few ourselves. We wanted to see, given all of this testing capability, how does one go about choosing which testing technique does best? And are there any differences between these different testing techniques for smart contracts? So I'm going to go through these different testing techniques, some of which is ours, and AF, or the SFuzz technique, I think it was in a paper from a year ago. I forget which conference, but one of the top software engineering conferences. And so we compared their technique as well. So the testing techniques we ourselves implemented, one is a black box fuzzing technique, Sol Analyzer, but there are some other tools out there as well that provide this capability. We also implemented a gray box fuzzing technique, which combines black box fuzzing and SMT solving, like in GPU kernels, but for smart contracts now. We also have a testing technique based on genetic algorithms. And finally, the AF technique is a cross between fuzzing and genetic algorithm that the SFuzz guys developed. And we use that tool as is in our empirical evaluation. So black box fuzzing, the way it works is that it goes through all the contract functions, and based on the interface that you have for this contract, which provides what inputs you need, what are the arguments to the functions, what are the different data types, you set random values for these parameters, respecting the ranges and constraints of the inputs, and you generate black box fuzz tests. Adaptive fuzzing, which is the SFuzz tool that exists already. This does something a little more clever. So what they do is that they initialize the seeds, and then they have this heuristic where if a new seed, which you generate by mutation, covers an extra branch, then you add it to the test suite. But it's not just a new branch. They check if it covers any just missed branch, and I'll show you what that means. So let's say you have a random seed and you execute this particular path. That's the first thing you execute. You've executed ABE. So the next test you add to the test suite is useful if it covers a new branch. But checking every new branch is an expensive process if you've done it before, because you have to instrument and you have to check if every branch condition was satisfied or not. So that's a costly process. So what they do is, to avoid this elaborate check, they only check branches that are a distance of 1 away, so 1 edge away. So in our case, a distance of 1 away is D, because it's only 1 edge away, and C. So if these two branches were covered by a new test, then you would add it to your test suite. Otherwise, you discard it and you keep mutating it. So the techniques we implemented, gray box fuzzing, is you take your black box fuzzing, run it for a while, and if you have uncovered branches, and I think we did uncovered branches. If there are uncovered branches, then we call the Z3 solver and try to cover the branches, and we combine the black box fuzzing tests and the tests from the Z3 solver. Genetic algorithms, we used opcode coverage as the fitness function. So we start off with an initial population, which is random values for the inputs. And then you check whether you've reached the stopping condition, which could be 100% opcode coverage. You sort the population based on fitness score, which could be on decreasing order of opcode coverage. You select the top 2 parents, select them for mating, do crossover and mutation, and check if the offsprings achieve better coverage than the parents, generate a new generation, and this is the typical algorithm for genetic algorithms. So there's nothing new, we just adapted it for Solidity contracts. So in our experiment, we had about 1,665 smart contracts that we collected from Etherscan. We also got contracts from a paper in, I think, ICSI 2019, where they had real contracts with vulnerabilities in them. So we took 90 vulnerable smart contracts, which had 5 different vulnerabilities in them. So we took both sets of contracts and we checked how well the different testing techniques covered the contracts and also uncovered vulnerabilities in them using the vulnerable C dataset. So we checked opcode coverage, call coverage, event coverage, and branch coverage. We seeded artificial false, so checked artificial fault finding and also real faults from the existing vulnerabilities in the vulnerable C dataset. And finally, we checked how long the execution techniques took, the test generation techniques took. So this is a bit hard to read, but here each graph shows different types of coverage, and every color is different types of techniques. So black box fuzzing technique, gray box fuzzing, genetic algorithms, and adaptive fuzzing. And this is a frequency plot. So if you just look at the medians that's shown here, which is the dashed line, you can see that the AF technique, which is the one here, has about just over 50% opcode coverage for the 1,665 contracts on average. The yellow line is GF, which is just below AF. So there was no significant difference. So we did run statistical analysis on it. And then after that comes BF, and then a little later comes GA. So it was a similar trend for other types of coverage as well, call coverage, event coverage, and branch coverage. So we measured different types of coverage, and the trend was similar. AF was always the best, but only marginally so. There was no significant difference based on the statistical analysis. The only significant difference was between the fuzzing techniques and genetic algorithms, and fuzzing techniques seem to outperform genetic algorithms in our experiments. So this same graph is shown for the vulnerable C data set, which is about 90 contracts with real vulnerabilities. So the main reasons, so what was surprising to us in this experiment was that the coverage was only 50%, and even call coverage was only close to 75%, and that's not typically acceptable. Coverage needs to be at least over 80 or 90%, which means there's significant parts of the contract that the tests do not execute. And that is a concern. So we went back and looked at the contracts, and we found that part of the reason was because we restricted input generation time. We only ran the test generation techniques for 15 seconds per contract. So we did try to increase our generation time, and you can see that coverage does increase, but it's not that it reaches 90% coverage. So it does taper off after some time. The improvements do start to plateau after some time. So it's there's still significant uncovered regions, but this was maybe part of the reason that it had so much uncovered contract regions, both call coverage, opcode coverage, branch coverage, and event coverage. Dependency between functions was one of the things that none of the techniques seem to take into consideration. What does this mean? Dependency between functions is, an example is shown here. There are 3 different functions in the smart contract: assign, approve, and send. Assign does something, okay? So it assigns this to true. The approve function checks if the assigned is true before executing something. And most test generation techniques test functions in isolation. They do not check if assign was set to a particular value before executing approve, and then send depends on the output of approve to be executed. So the if condition, it's quite clear if you look at the conditions within, but the condition only becomes true if the previous function was executed with a certain value. So this dependency was not taken into account by any of the test generation techniques. Finally, inherited contracts had unused functions, which was not considered as well. Modifier usage. So I'm going to skip through some of these things because I have 4 minutes left. So I really should be finishing. So anyway, the takeaway was that we did fault finding as well with artificial faults and real faults, and we found AF did better on, so there are different types of vulnerabilities that is shown here, and the AF technique did marginally better than GF, which is gray box fuzzing. So the conclusion was AF was slightly better than all other techniques, but there was no statistical significance. And all 4 techniques, the takeaway was that all 4 techniques need significant improvements to cover the contracts fully, and find the fault finding scores were not very high as well. So there's still a lot of work left in smart contract testing to get to where we really want complete trust. So that's all from me. I did have a slide with the URLs. Oops, I think I have. Sorry. So here are the URLs to some of our tools. Do check it out, and contact me if you have any questions about the tools or how to use them, or if you want to follow up on the work. Thank you so much. Any questions? Sorry, I took up all the time.
Thank you very much. Excellent talk. We still have a few minutes, so if there are any questions, we would be happy to. Yes, Alice, please. You're muted. That must happen once a day, right?
Yeah, it happens every single time, actually. So thanks for a great talk. That's really interesting. So your first technique, when you talked about the fuzzing and the SMT solver, would it have been possible to do it without the fuzzing at all, and just do the whole thing using the Z3?
Yeah, absolutely, you're right, and that is probably in an ideal world, that's what you should do. It's just that SMT solvers have a higher overhead in solving all the branch conditions. So the idea with fuzzing is that you give SMT solver lesser work to do. Okay. So rather than telling it go off and find me tests for 500 path conditions, you say you reduce it down to the interesting 20 or 50 that's difficult for fuzzing and SMT solver, because the overhead is much higher. It's about 10 to 50 times higher than fuzzing. So it's better you use SMT solving sparingly and for the interesting path conditions rather than all.
Okay, yeah, that makes sense.
Thank you. I think given the time, we could conclude now. And then, of course, if you have any further questions, please get in touch with Ajita later on. So thank you very much. It was a very interesting talk. And of course, we will continue having other interesting verifiability talks. So in 2 weeks' time, we will have Georgios Vainakos from Arizona State University, who has done very interesting work in certification of autonomous vehicles. So I haven't received the title from him yet, but I assume it will be something in that sphere. So please do join us in 2 weeks' time. Thank you very much for being here. And thanks again, Ajita, for having accepted our invitation.
You're welcome. Thank you.
Thank you.